comes to complex numbers, there's something called an Euler identity. Which says e to the I theta is same thing as cosine theta plus I sine theta. In order to prove this, you need to recall the Taylor series. So, does anyone remember the Taylor series of sine of x? X minus 1 over 3 factorial x cubed. What next? Next one? What's the next one? Plus, I mean, there's a pattern, right?
1 over 2 factorial x.
No. 1, 3, 5 factorial. And then minus. How do you get this? Well, Taylor series or Maclaurin series, they're basically saying that these functions that we know of, sine x, cosine x, e to the x, these are polynomials, but not really. They're like infinite polynomials, so you rewrite them as like a0 plus a1x plus a2x squared plus a3x cubed plus and so on, right? And then to get a0, you plug in 0 both sides. And everything disappears, you get a0 only on the right side, whereas what sine 0? Sine 0 would be 0, so you get a0 as 0, right? So once you get that, you see that a0 is 0. Now how do you get a1? You differentiate both sides. So sine differentiates the cosine x, and that becomes a1 plus 2a2x plus 3a3 x squared plus right? And now how do you get a1? Differentiate sine becoming cosine, x differentiates to 1, x squared differentiates to 2x, x cubed differentiates to 3x squared. So I get this identity. How do I get a1?
Plug in 0.
Plug in 0 again. So you get cosine 0 equals, all of these are 0 and you just get a1. What's cosine 0? 1. So you get a1 as 1. Right? So this is 1. Now what do you do? Differentiate yet again. So this differentiates to negative sine x. And that becomes 2a2 plus 3 times 2 a3x. Plug in 0 again, then you get a2 as 0, right? Differentiate again, then 3 times 2 times 1, that's 3 factorial, right? Which becomes negative cosine x equals to just 3 factorial a3. And then plus something x squared, and so on. You plug in 0 again, you get negative 1 equals to 3 factorial times a3. Divide, you get that, okay? You keep going and you get all of these. Okay? Now, the real fun part is that once you have this identity, then you're going to truncate this. This is too large. So let's say you take the first, like this much only. This much only. And you draw this graph, and you draw this graph. If you have a graphing calculator, please try this at home, okay? Yeah. Draw the graph of sine x and draw the graph of this, and look at near 0, they're almost identical. Okay? Of course, eventually they become different. That's because you've truncated. To get better looking sine graph, you just add more terms, and becomes better and better, okay? So, in fact, if somebody asks me what sine of 0.1, I can use this formula on the right side to give the approximate answer, right? What's that? That's 0.1 minus 1 over 6 times 0.1 cubed. And the next one's too small, so it's probably something like this. What's that? That's like 0.001 over 6, which is 0.00016666, right? And that's being subtracted from 0.1, so this will be like 0.00, no, 0.0998833. So that's the approximate value. Can somebody verify this using a calculator? Put your calculator in radian mode. Tell me what sine of 0.1 is in radians. What did you get? Yeah? Same thing, right? Yeah, okay. You get this much. Okay, so after looking at this in several different perspectives, you'll kind of agree that indeed sine x is the same thing as this thing. Right? Agreed? Okay. That's Maclaurin series, which is what you should have learned in Calc 2. But you guys were too busy just passing the test. You didn't really ask yourself what it was. But now you know, right? Okay, now you know what it means. This is important because this tells you how to get the approximate values of sine x. Okay. Okay. If there was a World War III and if everyone went nuclear and only a handful of people survived and with no technology, how are you going to rebuild all your sine tables? This, okay? You can rebuild the entire sine tables by using this. Okay, so that's the Taylor series or Maclaurin series of sine x, and of course, the cosine x, you could do the same thing, but the faster way is to simply differentiate this to get the result for the cosine x. So if you differentiate x, you get 1. 3 comes down when you differentiate, but one of the 3's will cancel, so you end up with 1 over 2 factorial x squared. 5 cancels, so you have 1 over 4 factorial x to the 4th, minus 1 over 6 factorial x 6th, and so on. So that's the cosine. Okay, does anyone remember the Maclaurin series of e to the x? No, okay. This is 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed plus 1 over 4 factorial x to the 4th, so on and so on. Okay? What's the derivative of e to the x? So this right side better give you the same thing if you differentiate, right? So let's see. If you differentiate 1, that's gone. If you differentiate x, you get 1, right? If you differentiate x squared, 2 comes down. 2 factorial is 2. So that's just going to cancel out, and therefore, derivative of this is going to be same as that. You get it? Yeah. When I point to things like this, you really want to follow what I'm saying by using mental math. Okay. The difference between being able to do mental math or not is night and day. Okay. If you can't do mental math, then you're always behind to those who can do the mental math. Right? So just keep training your mind to do mental math. If you differentiate this, 3 will come down, right? X cubed differentiates in 3x squared. And that's going to cancel one of the three. Remember, 3 factorial is 3 times 2 times 1. So that 3 cancels out, leaving you with 2 factorial, right? So what happens if you differentiate this? You get exactly this. What happens if you differentiate this? 4 comes down, getting rid of the 4, you get exactly that. So what does that mean? If you differentiate the right side, do you get anything different? No, you get the same exact thing again, right? That's why this right side has the same property as the left side. Okay. In fact, you're going to learn later, the follow-up class to this one is differential equations, right? So you're going to learn that a function whose derivative is same as itself and its value at 0 is 1, right? If you plug in 0, you get 1, right? So this right side, I mean, what I'm trying to say is that suppose that you didn't know this was e to the x, and you just call this some function, okay? Now this function satisfies two properties. The derivative is same thing as itself, that's what we just observed, right? And if you plug in 0, you get 1. You're going to learn later in differential equations that the only function that satisfies both is e to the x. Obviously, right? And can you think of anything else that satisfies those two properties? E to the x is special because if you differentiate, it's the same thing, right? But of course, any multiple of e to the x also has the same thing. So the solution of this in general is some constant times e to the x, but that constant has to be 1 for this to be true. So you end up saying that this has to be e to the x. So that's another way to verify that these two are the same, but of course you can plug in values to get the results as well, right? Okay. So now we can go back to this, what I was trying to say, okay? So let's just take this identity and replace x by I times theta. So set x as I times theta. That makes e to the I theta equal to 1 plus I theta plus 1 over 2 factorial I theta squared. See, every time I see an x, that's going to be replaced by I theta, right? Plus 1 over 3 factorial I theta cubed plus 1 over 4 factorial I theta fourth and plus that. Just keeps going. Right? And then we use the fact that I squared is negative 1, so that's going to be negative 1. So it's going to be 1 plus I theta minus 1 over 2 factorial theta squared. And then I cubed, what's I cubed? I cubed is I squared times I, so it gives you negative I, since I squared is negative 1. So that's going to give you minus I, 1 over 3 factorial theta cubed. And I to the fourth would be I squared times I squared, so that's negative 1 squared, so that's just going to be 1. That's what you're going to get. And yeah, let's just do one more. The one that's after this would be 1 over 5 factorial I theta to the fifth power, and that's going to be plus I times 1 over 5 factorial theta to the fifth power. Now we're going to collect the real part and the imaginary parts. The real part is 1 minus 1 over 2 factorial. I'm just identifying the ones without I. So these three do not have I attached. Plus, there's this other part with I attached. This one has I. This one also has an I. If I get rid of the I, it's minus 1 over 3 factorial theta cubed. And then if I get rid of this I have 1 over 5 factorial theta fifth, and so on and so on. Okay. Now what do you see? What is this same thing as? Cosine, right? That's exactly cosine theta. What is this same as? Sine. All you need to do is just look at here and just replace all the x's by theta. That's exactly what you get. Okay? So you see that e to the I theta is equal to cosine theta plus I sine theta, which is known as the Euler identity. Now, Euler identity allows you to look at the complex numbers in a whole new way. In fact, it makes some things very obvious. So, if you recall, uh, last time I said the following, that if you have a plus bi, you can rewrite this in terms of the polar form. Okay? And I also gave you the formulas, right? R is equal to square root of a squared plus b squared. And theta is equal to arctangent, or tangent inverse of b over a, plus some alpha, where alpha is 0 on the right side, but pi and negative pi on the left side. That's what alpha is. So that's what I explained last time, but do you see that this now can be written as e to the I theta, right? So we can say that a plus bi can also be written as r times e to the I theta with the same formula for r and theta, okay? And this form is called the Euler form. I also mentioned that if you multiply cosine A plus I sine A with cosine B plus I sine B, that's going to give you cosine A plus B plus I sine A plus B. And I had to use geometry and the transformation of points and all that to explain why that was true. And that looked quite complicated because you see so many sines and cosines. But see how simple it is if you wrote the same thing in terms of the Euler form. See, what is the Euler form of this? E to the IA, right? That's the identity. Instead of cosine theta plus I sine theta, I can simply write e to the I theta. Right? So all I have to do was replace this by e to the IA and multiply that by e to the IB for the same reasons. And what about this one? E to the I A plus B. Now look at this. It's obvious, right? Because you know that if you have e to the x times e to the y, what's that? E to the x plus y, right? Right. It's obvious. So if you do IA plus IB, of course that's what it is. Right? What looked very complicated, which required lots of geometry and other stuff to explain, this looks obvious if you look at it in terms of the Euler form. You get that? Okay. Let me write another thing, which is if you have cosine theta plus I sine theta to the nth power, then that's going to be equal to cosine. Don't write this part. I just want to explain it and read it. This will be cosine theta plus I sine theta multiplied to itself many times, right? Cosine theta plus I sine theta and cosine theta plus I sine theta. So, but then every time you multiply, what happens to this? This would be theta plus theta, so it's going to be cosine 2 theta plus I sine 2 theta, right? And then you multiply the next guy, and there's another theta here, so if you add them here, you end up with cosine 3 theta plus I sine 3 theta. And keep doing that. If n is like 100, then you keep doing this, racking up all the coefficient of theta, you end up with cosine 100 theta plus I sine 100 theta, right? So because of all that, we know that this is going to end up being equal to cosine n theta plus I sine n theta. And because this was used in several other places, people honored the person who found this. It's called de Moivre's theorem. Okay, if you take the cosine theta plus I sine theta to the nth power, that's what you get. That's called de Moivre's theorem, which looks very fancy, but if you know the Euler identity, this thing above is obvious. What is this saying if you write in terms of Euler identity? That's what it's saying, right? The right side can be written like this, the left side can be written like this. And if you have an exponent and another exponent, these two multiply, so of course that's what it is, right? So Euler identity makes several of these magical identities in complex numbers very natural. Okay? Multiplication revisited. So in polar form, you have R1 cosine theta 1 plus I times sine theta 1. Let's say you have one number like this and another number R2 cosine theta 2 plus I sine theta 2. And when you multiply them, you get R1 times R2. And then cosine theta 1 plus theta 2 plus I times sine theta 1 plus theta 2. That's what we get. Okay? And it's basically saying that I'm multiplying R1 and R2, and the angles add, which was something that I explained last time, right? In Euler form, this is this much can be written like this can be written like this, and it's saying that the multiplication of these two are R1 times R2 e to the I theta 1 plus theta 2. This looks very fancy, but this is kind of natural. In Euler form, it's obvious because that's how you multiply exponents. Yes?
If you were to like ask a question about this topic, like how would it be set up?
Yeah. So, for example, okay. Yeah, I think I should be putting an example question. Okay. So, good point. Suppose z is equal to 1 minus I. Compute z to the 10th power. Okay, solution. Uh, Surprisingly, it's not so hard to do it directly. Okay, there's no fun in that, but let me say it's solution one. But I guess, let's make this 20 so it's a bit more challenging. Say z to 20. That'll make things a bit more challenging, right? Okay, so let's start with z squared. There's 1 minus I times 1 minus I, which is, what's that? 1 times 1 is 1, 1 times negative I times 1, negative I times negative I. That's actually minus 1. So these cancel, you just get negative 2I. That's going to allow us to do z to the fourth power, which is negative 2I squared. So if I square both sides, z squared is squared with z to the fourth, and you get this squared, which gives you 4 times I squared, but that's negative 4. Okay? Now we square this again. That's going to be 16, right? And then we square this again. Squaring z to the 8th will double the exponent, so z to the 16th power, so that's going to be, what's that? 16 times 16 is 256, right? Okay, so we're almost there. Since z to the 20th power is equal to z to the 16th power times z to the 4th power, that's going to be 256 times negative 4, which is going to be negative 1024. That wasn't too bad, was it? It's doable, yeah. Solution 2 would be, I mean, you could also use the formula for it, but in many cases, it's easier to just draw it. So what is 1 minus I? That's, you go one step in the real direction, and then you go negative I in the imaginary direction. It's this one, right? Okay, give me the R and the angle theta. What's R? No, this is 1 and that's 1, so if you do Pythagorean 1 squared plus 1 squared square root, that's going to be square root of 2. Yeah. Okay. And then what about the angle? Well, angle is, I know that it's going that way. What is this angle? Kind of obvious from the picture, right? What's the angle?
45.
45 degrees, but it's going in the negative direction, so let's write negative pi over 4. Okay? So that means z can be written as square root of 2 times e to the negative pi over 4I. Yeah, sometimes it's easier to put the I later. Usually constants you put before I. If it's some function, then you put it after I. Okay. So now we take the 10th power, or 20th power. Okay, so what are we getting? This is square root is half power, so this is 2 to the 10th power. And this is going to be 20 divided by 4 is 5, so it's going to be negative 5 pi I. And then What is 2 to the 10th power? 1024. You can just 2 times 2 times 2 times itself. You can get that. And then what is negative 5 pi? Well, negative 5 pi would be, see, this is pi is a half circle, right? So you go 1, 2, 3, 4, 5. Where are you? Negative 1. So we see that this is going to be equal to negative 1. This is going to be 1024. Therefore, the answer is negative 1024. Okay.
How did you get -1 for e to?
Oh, negative 5 pi. So e to the pi I is what? This is, pi is this angle, right?
Yeah.
So you get a number that's in this direction of size 1. This will always have size 1 unless you have something multiplied in front, right? Yeah. So going this way, size 1, that's negative 1.
Mm-hmm.
So that's negative 1, right?
All right.
So now if you want e to the negative 5 pi I,
Just do that.
actually it's going this way, right? So it's 1 pi, 2 pi, 3 pi, 4 pi, 5 pi. This is negative 5 pi. That's negative 1.
So e always is has a magnitude of 1.
Yeah. So because you have e to the I theta equals to cosine theta plus I sine theta, this always lies on the unit circle. So this has a magnitude of 1, right?
Yeah.
Therefore, this will always have a magnitude of 1.
All right. Thank you.
Yeah. Example 2. Let's try the following. Let's say z is equal to negative 1/2 plus square root of 3 over 2i. Okay. And this time, let's say you want z to the 100th power. Okay. Just to discourage some people. Right. Let's think about this. It's negative 1/2 would be the real part. And radical 3 over 2 will be the imaginary part. So this is the number, okay? Notice that they square to add to 1, so it lies on the unit circle, right? Do you remember that these are like special values of sine and cosine, right? So can you tell me what this angle is?
120 degrees or 2 pi over 3.
120 degrees, 2 pi over 3. Okay. So solution would be that z is equal to e to the I times 2 pi over 3. Now you take the 100th power. Well, rather than that, let's just take the 3rd power. That's easier. So what is e to the 3rd power? E to the I times 2 pi over 3 to the 3rd, 3 cancels, right? So you get e to the 2 pi I. What's that? You've gone around the full circle, right? You're here. What is that? What's this value? What's this value? 1. In fact, if you took the time to multiply this to itself to calculate z squared, and you multiply this again to z squared, which I don't want to do, that takes more time than this, okay? You will find that you get a 1, okay? Yeah, it will be 1, yeah. It's surprising, but you'll get the same result, okay? Oh, but what does that mean? That means z to the 99th power is equal to? This is z to the 3rd power to the 33 power, right? What is z to the 3rd power again?
1.
1, so 1 to the 33rd power is? 1. Therefore, what's the answer? Z to the 100th power is z to the 99 times z. And because this is 1, we have the z, which is negative 1/2 plus or equal 3 over 2 pi. Done. That's the answer. Okay. without having to do a single FOIL. Yeah, you get the answer. Isn't that cool? Kind of nice, right? Okay, so that's the power of the Euler form. Why? You don't trust me? Should we redo this using FOIL?
No, I'm just confused how like is that the circle that's the answer?
Yeah, that's the answer. Yes.
So the thing that you begin with
Yeah, if z is this, z to the 100th power, which means you multiply this 100 times, you get that. I mean, okay, solution 2. If you don't believe me, we can try this out, okay? So negative 1/2 plus radical 3 over 2i times negative 1/2 plus radical 3 over 2i. This time this will be positive 1/4. This time this will be minus radical 3 over 4i. This time this will be another radical 3 over 4i. And this time this will be, well, I squared is negative. Radical 3 squared will be 3. 2 times it will be 4. So you end up with negative 1 minus 3 will be 2 over 4. And then minus 2 radical 3 over 4i, which is negative 1/2 minus radical 3 over 2i. Okay, so that's what we get. And then let's compute, this will be z squared, right? So this will be z squared. Z cubed is z squared times z, which is negative 1/2 minus radical 3 over 2i, times negative 1/2 plus radical 3 over 2i. Now, notice that this is a product between conjugates, right? These two are conjugates of each other. Okay? If you have two things that are conjugate, you can use this formula a minus b times a plus b. What's the identity here? If you multiply a minus b times a plus b, you get a squared minus b squared. Yes, that's what you get. So I can apply it here. You get negative 1/2 squared minus radical 3 over 2i squared, which is positive 1/4, minus, and then there's another minus, so it's a plus. I squared gives you another minus. Minus minus is plus. 3 over 4, which is 1. Aha. So I get z cubed equals 1. Okay. And the rest is exactly the same. Once you get z cubed equal to 1, yeah. Notice that we did so much more work than here just to get z cubed equal to 1, right? But once you get z cubed equal to 1, then z to the 99 will again be 1 because you keep multiplying this z cubed, you always get 1. So even if you repeat that 33 times more, you still get a 1. And therefore z to the 100 is z to the 99 times z, which is again the same. Okay, so you can do it by foiling. Yeah. But Euler is definitely better this time. Okay? You would agree, right? Yeah. Okay. So going back to our discussion. The discussion is that if you view things in polar form or the Euler form, then multiplication is a lot easier to do because you don't have to FOIL. If you do it the rectangular form, somebody asked me, is this also Cartesian form? And the answer is yes. So rectangular Cartesian form, you actually have to FOIL this out, so it takes more effort, whereas multiplication in this way, it's not simple. Okay. All right. Now, let me add to this another notation, still another notation, which is, I would call it shortened polar form, which is to simply write either this or that as R1 angle theta 1. Okay. Okay.
I have a question that's kind of separate from that.
Yeah.
When you have R1 e to the I theta
Uh-huh.
times R2 e to the I theta,
Yeah.
why do you not get e to the 2I? So
Okay. Yeah. So I theta 1 has to be added to I theta 2, right? And you're really factoring the I out. If you factor the I out, you end up with theta 1 plus theta 2.
that's it.
Yeah. So that's why you get that. All right. So the shortened polar form, and interestingly, if you show this to any of the mathematicians who are not used to interacting with the engineers, I think all of our faculty here would know this form, but many people who are just math majors wouldn't know this symbol because this is something that engineers came up with. So it's a nice shorthand for either of these. Okay, so these are the same thing. So it's just writing down the magnitude and then angle. Yeah, which is quite neat, right? Yeah. So if you take this shortcut, shorthand polar form, then R1 angle theta 1 times R2 angle theta 2 is R1 times R2 angle theta 1 plus theta 2. And this actually gives you a simpler view of what's happening. When you multiply two complex numbers, what's happening is that their magnitudes multiply, but their angles add. That's what this is saying. Okay, so both of these, they might look a bit complicated, but if you write it in this shorthand, it's kind of obvious what's happening. The magnitude, the sizes multiply, but the angles just add. That's what it's saying.